Thank you, and welcome to the last colloquium of the semester. It's my great pleasure today to introduce Professor Zhang as our colloquium speaker. Professor Zhang received his bachelor's and master's degrees in China and then did research at the Max Planck Institute for Solid States and received his doctoral degree in physics from the University of Stuttgart in 1991. He then worked as an assistant research engineer at the University of California at Santa Barbara before he joined the Hughes Research Labs in 1993. And in 1996, he was appointed an associate professor in the Department of Electrical Engineering at ASU and was promoted to full professor in 2000. He is the founding director of the Center for Photonics Innovation at ASU and is a fellow of the OSA. His areas of research include MBE growth, optical properties of semiconductor heterostructures, optoelectronic devices, and their applications. And I'd like you all to join me in welcoming Professor Zhang.
Thank you. Let me turn this on. I guess, let me see. Is this on? All right, thank you. Yeah, thank you, Matt, for the introduction. Probably I should stand on the other side. Yeah, it's always a great pleasure to visit U of A. I think I don't remember. This is my maybe fourth or fifth visit to U of A. And so today I would like to share with you some of our recent results generated through a MURI program, basically to study this kind of okay. This indium mask, so-called gallium-free. So I will explain why we call it gallium-free. The indium arsenide, and antimonide type 2 superlattices. And before I do that, okay, maybe, let me see. Maybe I'm too far. Sorry. All right, I just, manual control is always better. Yeah, before I start, I should acknowledge the contributors. Many of them have already left the group. Oh, thank you. Many of them have already left the group. And in particular, I just want to thank my previous postdoc, Olkan Selek. He's now working for a company in California. And my previous postdoc, Ding Ding, for MBE. And of course, there are many people who process the devices. And the other important contributor is my previous PhD student, Elizabeth Stingberg. And right now, she's working for AFRL on the same topic. And then we have a student like Jing Fan now working for Soytech Phoenix Lab, working on CPV solar cell system. And now these are the current students and some of my collaborators like Shane Johnson, Jacek Ferdina at Notre Dame, Xingyu Liu, and David Smith. All the beautiful TMs from David Smith. So that's very well known. And of course, the funding agency who have written a lot of checks for us, so we have to thank them. So it's a really great support. Say like the MURI program is just wonderful, and also I got a lot of support from Science Foundation Arizona for solar cell part, but not for this part. Okay, first I just want to spend a few minutes to give you a general introduction, because I understand there are some students here. So basically here you can see this is electromagnetic spectrum. So, and this covers a very broad range, of course, start from gamma ray and down to terahertz or very, very low frequency, like electrical power. But obviously, we human beings can only see very, very small, band in this huge spectrum. And of course, we want to see more in other bands, for instance, in infrared. And so in the infrared, you can see, so typically we call this near infrared, like 800 nanometer range. Then we have a short wave infrared, like below 2 micron. Then we have a middle wave infrared from 3 to 5, then 8 to 12 or 8 to 14. We call this a long wave infrared. Or then beyond that, people call this a very long wave infrared. So this is a very broad spectrum range. You can do all kinds of things. For instance, for the visible, of course, you can see beautiful flowers. Then near infrared, basically you can see, say for instance, where you have moonlight, the light is not very strong, but you can use say like so-called photo multiplier, then you can still see very light in the dark. But if you have even no moonlight, absolute no light sources, so what can you see? Then you can only see the black body radiation, like from human body. So then it's not near infrared, it's a long wave infrared. So because our human body temperature is 37 degrees Celsius and 97, I think, Fahrenheit. I always have to translate into Fahrenheit. So there it must be a long wave infrared. Then you can really see. And so that's why, for the defense application, they always interest in multiple bands. Now, of course, you can also find other applications like chemical sensing. So the basic principle is very straightforward, is that many of the chemicals, they have absorption, very sharp absorption peaks in the middle infrared range, okay, in the middle range, due to the molecule vibration modes. And here is just a list of some molecule, for instance, carbon monoxide. And so they have very strong absorption, 2.3, 2.4. And then you have, carbon monoxide and 2 microns, so on and so forth. So by monitor this, you can really help either industry or environment to understand what kind of environment it is. For instance, we were talking about, the future iPhone. I personally believe you should have some of the sensors, built in, because these sensors can be very cheap. If you use a semiconductor, and then you can walk into a room and say, "Oh, the air in this room is not clean. I better get out of it." Right? So I think people are willing to pay maybe $5 or $10. I would, if you because I pay $300 for the phone, right? So these kind of things, I personally believe, will eventually get into our daily life. I think it's not an impossible thing. Then of course, what kind of sensors can we have? So for all these things. So here is kind of a quick summary of all kinds of infrared sensors. Okay, this can be for imaging or just can be for regular sensing. So typically, you have two kinds of category of sensors. One is the thermal detectors. The other is the photon detectors. And thermal, basically, you detect energy. So like you have bolometer, which can operate at room temperature. And so it's, integrated with, using MEMS technology and read out the circuits. All right, so this is kind of a low cost. It can be low cost, but it's relatively low performance because you measure the heat, basically, the heat. Now, the other is a photon detector. Then you could have a kind of two types of photon detector. One is a so-called a band-to-band transition photon detector, and then the other is kind of intra-band excitation photon detector. So this one we're not going to cover today. These are all well-known, like a QUIPS, quantum well infrared photo detector. Basically, this excites electron from the ground state of one quantum well energy level to the other one, or the continuum state, then they can transport. Or this quantum dot infrared photo detector, similar operating principle, or Schottky barrier, you excite electron to go over the Schottky barrier to contribute to the current. So today we basically focus on the band-to-band excitation detector. Then you can have many kinds. So most commonly, people use these bulk materials like either indium gallium arsenide or mercury cadmium telluride, which is middle infrared, a long wave. This is short wave. So the indium and timolite, this is a middle infrared, right? So you can see all these. So like this one can only work within the short wave. So this is working in the middle infrared and long wave. then this one is only emitting infrared. So the mercury cadmium telluride is a very good material for detector. It's probably one of the best material for photo detector. But there's always a price to come with it. It's very expensive. It's very, very expensive. And if you grow on lattice matched substrate, which is cadmium telluride, and it will cost you $2,000 per square centimeter. That I was told. Very, very expensive substrate. So that's why people have been wanting to developing a alternative technology, which not only offer the performance but also the lower cost. The other disadvantage of this mercury cadmium telluride sensor is the uniformity. The uniformity. So especially these days now, people are making larger and larger focal plane arrays. So the uniformity becomes very, very important. Okay, it's more important sometimes than the individual pixel performance. So obviously, the 3.5 semiconductors has much better uniformity than the mercury cadmium telluride. And so multiple reasons people still want to develop these 3.5 middle infrared, long infrared detectors. Then, of course, lasers as well, because sometimes these two devices come together. As I mentioned, this chemical sensing. You need an emitter and a detector. So obviously they come together. Okay. So that is the overall background of why we want to study this. And here just kind of summary about the performance of these devices. So I said that already. So this one can operate at room temperature, which is an advantage, but the performance is much poor. So, but this one has much lower quantum efficiency, and also you have to cool it down to very low temperature. So we're going to focus here. Basically, we want to have a high performance and a device which can operate at relatively high temperature. Okay. To summarize what I said, I just put some bullets here. I probably don't have to read all of them. So basically, just want to show you the image taken by these different sensors. And let me see. Here are some kind of numbers. Let me see. Yeah, the MCT is a really wonderful device. You can get a high quantum efficiency, 60%. This is very impressive. And the QUIPS, the efficiency is very low. It's only 5 to 10%. And then so we hope that this type 2 can reach 60% as well, but we're not there yet. And so, yeah, the uncooled, of course, much poor performance. Yeah. All right, to summarize this, I think you can see what I just said earlier, the comparison of these devices. And so this is just a table. Now, the other thing is that since I come from engineering school, so I always, put some consideration to cost. Sometimes I think that's probably the difference between we do research from engineering point of view versus from physics point of view, because we have one more parameter to optimize. That is cost. So when you add that parameter into our research, you will see the approaches will be very different. Okay. So the optimization from engineering point of view is that the cost. And now the cost of the infrared system actually comes from the cooler. Right, so here just tells you how much this cooler contributes to the overall cost. So for instance, if you want to go to long wave infrared and you have to cool down to a low temperature, the cooler is very expensive. So that is the reason that we want to have detectors which can operate at just slightly higher temperature. Even say 5 degree or 10 degree higher in operating temperature, you're going to save tremendously from the cooler cost. Right? So that's another reason we want to optimize our sensor to make it operational at a high temperature. Okay? So this is from the technology point of view. Okay, so that was the background, and so now I just want to probably discuss a little bit about I call it the past of type 2 superlattices, and basically the kind of history. So I think you probably all know that the concept of superlattices was first proposed by this well-known scientist, Leo Esaki and Ray Tsu from IBM that time. And so they were working on actually electronic devices, but they come up with this idea. Then later on, I think it's getting more popular with the optical community than the electronic community. So they proposed, two types of superlattices. One is a type 1, the other is a type 2. The type 1 you can see. So the electrons and the holes will be confined in the same region, and for the type 2, they are confined in different region. So like this is the well for electrons, then here is the well for holes. They're in different region. So that time they call it type 2 superlattices. And then in a few years later, almost 10 years later, and they pinpoint their idea to this material system, indium arsenide and gallium antimonide. And so they published a very nice theoretical paper to predict a lot of things. But again, that's more on the electronic device application rather than optical. Now, since we want to use this to make optoelectronic devices, lasers and photodetectors, so now we can see the optical transitions in type 1 is very straightforward. All right, you have electron state and the hole state. You have optical transition between them. And for the type 2, so from high level point of view, is basically you can say, okay, the carriers, electrons and holes are confined separately in the space. So the optical transition, you can say, is optical, is spatially indirect transition. Okay. Even though the encased space they can be direct, but spatially they're indirect transition. So now here's a diagram which summarizes a lot of semiconductor materials, and which actually tells you so what kind of material combination give you type 1, and what kind of combination give you type 2. So this is a diagram. So I just walk you through a little bit. So let's focus on the blue lines. That is the 3,5 semiconductor. So now you can see around the gallium antimonide substrate or indium arsenide substrate, we have aluminum antimonide. We have also indium arsenide antimonide alloys, right? So if you look at this band edge alignment diagram, so now you can see. So this is a gallium antimonide, and this is the indium arsenide. So these two materials come together will give you type 2 alignment, because the valence band edge of gallium antimonide is above even the conduction band, edge of indium arsenide. And also, so is indium antimonide and indium arsenide. They will form a type 2. Again, this valence band edge is above that. All right. So, and also the indium arsenide and aluminum antimonide give you a type 2 arrangement, alignment as well, right? You can see. So this valence band edge is here, and valence band edge of indium arsenide is there. Okay. So this is a very helpful diagram to help you to see the band edge alignment. So then later on, I will, since I'm talking about this diagram, so later on I will also introduce some of our recent researches that now we can put actually the 2,6 materials on 3,5. Right, the 2,6 are linked by these pink lines. For instance, you can put a zinc telluride on top of a gallium antimonide, and they are very beautifully lattice matched. So by combining of these two material families, now you can imagine you can do really a lot of things. Right? Because first, you look at this band edge coverage is huge, from almost UV and down to far infrared. And also you have a very high mobility gallium antimonide, both electron and hole mobility, as well as indium arsenide. You can actually make a very, very low power electronic device out of this material system. So we, yes, we use MB.
So how do you heat up substrate?
Just a thermal heating.
But I mean, 2,6 is dopants for 3,5. So what do you
Okay. Yes, right. We have two chambers. Yes, yeah, we move them around, right. But now we have some very interesting ideas. I'm trying to build a novel MB chamber, just one chamber. We can handle both. So yeah, so I'm trying to raise money. So yes, so hopefully we can set it up. But right now we're moving them around. Yeah. All right. So So today I probably will focus on this type 2 superlattices. So this is a very nice summary chart, and probably too busy for most of you. So this just summarizes what happened in the history. So the type 2 superlattices started very early in like 69, 1970, and then the idea to use this for infrared detectors actually happened in the early 80s. But now, since we focus on this indium arsenide, antimonide superlattices, so the history for that, it was very interesting. Actually, some of the similar ideas was proposed by Sandia National Lab. That time I was at Hughes Research Lab. I think I was working together with Alan at that time. We were funded by Air Force Research Lab to develop middle-infrared lasers. And so during that period of time, I realized that so these superlattices can be very, very good for lasers. Because you can put this on indium arsenide or on gallium antimonide, and also you have the right strain to reduce the threshold. So basically, I think I started at Hughes working on this material system, but it's very, very interesting. So that I left the group in '95. But somehow after that, this idea was basically abandoned. I think nobody really tried. So I think George Turner at the Lincoln Lab, they tried a few rounds, but then they stopped a year later. So maybe 4 years ago, so that was merely a call for proposal. So I read that as a, geez, people are still want to demonstrate type 2 similar infrared detectors, because I was out of that field since I left Hughes. So basically, I never worked on type 2. So that's okay. I have this old idea, so I proposed that. Then the ARO, they somehow they liked it, so they picked my team. So we got this program. So it's very interesting, right? So I think it stopped '95. Then actually picked it up by a Canadian group, 2009. So you can see between these 95, 96, very basically no paper. So until '09, there's a MOCVD paper talking about that. So you see that it's sometimes very interesting. So later on, we'll tell you why the community got quite excited with this material system is because the lifetime we demonstrated 2 years ago. All right. So now, as I said earlier, there are two, at least you can find two ways to build this type 2 superlattices on gallium antimonide. One is using this indium arsenide, indium arsenide or indium gallium antimonide. Or the indium arsenide and indium antimonide, of course, by adding arsenide into it. So now to summarize the advantages of them, you can see for this material system, of course, you don't have a gallium there. That's why we call it gallium free. So later on, I will say why gallium is important. And so basically, you can see this material system interface is very simple. So the interface, you can only have 3 elements. Right, so the interface is much simpler than this interface. So this interface, you could have 4 elements, so you can have all kinds of combinations of the chemical bonds. All right, the number 1. So this is good, and so because I'm a grower, so this obviously is much easier to grow. All right, when you add 1 more element, you get more than just 25% headache. And now this one has a larger valence band offset, which actually sometimes good or sometimes actually it's not good. So it depends on how you view that. And now, so basically, we believe this one has a much less short radar recombination. So we have kind of a hand waving argument for that. And this one obviously has a very high short radar recombination rate. Okay. Now the cons is that, okay, so this one has a lower absorption coefficient, okay, due to the effective mass and wave function overlap, smaller effective mass and a smaller wave function overlap. And so this one has very short minority carrier lifetime compared with this one. Okay. So now if you plot the effective band edges, so you can see, so the effective band edge of this type of superlattices is somewhere here, and for the valence band edge is somewhere here. Now for this gallium antimonide based or the indium arsenide, indium gallium antimonide based, you get conduction band edge here and here. All right. So later on we will come back to this diagram to explain why we believe this material system offers much longer lifetime than this one. All right, so I just want to show you some of my previous results, and this was done in the middle 90s. So this is at that time actually the antimony cell was not okay. The antimony cell we use at Hughes Research Lab, just a conventional design. There was no valve to control the flux. So it's very difficult to grow this so-called group 5 alloys because the ratio between arsenic and antimony is very difficult to control. So at that time, I had to use this so-called modulated MB method. I use shutter operation to control the flux. But nowadays, we have this valve-controlled antimony cell, make our life much easier from the growth point of view. But anyway, so here's just some figures to show you that if you do this modulated molecular beam epitaxy, you're going to introduce additional superlattices in the superlattice. So those are the cell peak of those short period superlattices you can see. So this is a TEM. So you really can see this this modulation. This is only 10 nanometer. So you can see. So the modulation is very, very, very fast. But the TEM can really tell so very nicely. Actually, I think this picture was done by David Smith 3-4 years ago. So using my old Hughes sample. So I'm very pleased. After almost 18 years, we can still see this very nice thing. So now here is a quick summary about the strain, because in the very beginning the structure was grown on indium arsenide substrate. So when you have indium arsenide antimonide, which has a larger lattice constant than the substrate, you get this compressed strain. So that, of course, the band edge shifts accordingly. So this shift actually enhance the so-called type 2 alignment. You can see there's light, the heavy hole just moves up, and this conduction band also increases up. Okay. All right. So this is actually one of the very few photoluminescence excitation spectrum in the middle infrared range. And I think this is probably the only one I personally know. So this measurement was done by Frank Fuchs at Fraunhofer Institute. I think that he has, at that time, he has the only actually PLE setup which can cover middle infrared. So I talked with him actually a year ago. He said, so that system doesn't exist anymore because we move into other field. So it's very nice. The PLE actually measure the PL intensity by scanning the excitation wavelengths. So basically you can see the absorption spectrum simply by measuring luminescence strengths. So this is non-destructive. It's a very easy measurement. So it's a very powerful tool. So this just tells you that this is a PL peak of your type 2 superlattices. So you can see the absorption onset has some kind of a shift. And this is a strong indication or evidence that indeed you have type 2 alignment. Okay, so this also, because the type 2 absorption coefficient, you can imagine that even though in real space they are type 2, in K space they are still direct bandgap semiconductors, okay, both indium arsenide. But from theory, you can actually calculate that for the type 2 superlattices, it actually behaves very much like indirect bandgap semiconductors to a certain degree. Okay, so this shows you how the separation of the PL and onset of absorption. Okay. So it's a very, very interesting measurement. Now you can see by changing the different periods of the superlattices, you can cover different wavelengths. So I think this is the strong advantage of the type 2 superlattices, because we all know. So if you use like a bulk semiconductor or even quantum well, and so the band gap energy is basically determined by the nearest band gap of the constituent semiconductors, right? But you cannot tune it much. Well, of course, you can change the well width. You move the confinement engine up and a little bit, but you can never go below the band gap energy. Okay, so the type 2 superlattice, one of the key advantages, you get one semiconductor with this kind of band gap, you have another semiconductor with another band gap, you have this kind of alignment, but an optical transition happens between them. So the effective band gap is independent of this and this semiconductor. So this effective band gap is only determined by the alignment, right? For instance, if you have this alignment, this band gap is very small. If you have this kind of alignment, this effective band gap can be a little bit larger. So this gives us a tremendous freedom to tune, okay, the detection wavelengths. This is one of the most important advantages of a type 2 superlattice. So now we are not confined by the band gap of these constituent semiconductors. Okay, so that's why the type 2 becomes very, very important. Okay, so I think the early on, my first sample was grow indium arsenide. I think I grow a laser structure. So to cut a long story short, and I just want to show, indeed, using optical pumping, we demonstrate laser. So I believe, I think the Hughes team, that time from 93 to 96, I believe. I think the Hughes team was the first team in the world that demonstrated the type 2 superlaser lasers. And before that, people were always skeptical. Say, oh, type 2, it's good for detector, and probably not very good for lasers. But Hughes, I think that team demonstrated lasers using both material systems, indium arsenide, and indium gallium antimonide, and indium arsenide, antimonide. So it was a very, very interesting work. So I think that was probably one of the most exciting time I personally had at Hughes. So, right. But of course, as I switched to other projects, I was not that much interested in that. So I was much more interested in this one than the other one. Yeah. Anyway, so this is the lasing spectrum. You can see up to 126K. You can see a 3.8 micron laser. So anyway, so that was kind of past. And so I just want to spend most of the time from now on just talk about the current research. So I will focus on this indium arsenide, antimonide type 2 superlattice IR detectors. And now you can see if you just by changing the layer thickness as well as the composition of the indium arsenide antimonide, so basically you can see we can cover the very broad wavelength range, from 4 micron up to 12 micron. Okay. So it's a very, very broad range. But of course, and because of the type 2 alignment, when you go to longer wavelengths, let me see, the longer wavelengths, yeah, this green line, okay, this longer wavelengths, the wave function overlap, okay, a wave function overlap between the electron wave function and the whole wave function is getting smaller and smaller, right? Because it's more and more so-called more and more type 2, more and more type 2. The wave function is much more confined. All right. So this green line give you the 12 micron, the red line give you 10 micron, this gives 80 micron. So this is the wave function overlap. So you can see for the 12 micron, so the wave function overlap is much smaller, and for the conventional, say, quantum well, the wave function overlap is almost 100%. So here you can see only 10%. Okay, the square of the wave function overlap. So that will be this phenomena will be this fact will be reflected in the absorption coefficient. Later on, you will see. So the type 2 superlattice has a smaller absorption coefficient, right? So you see that the nature always asks you to pay some price if you get certain freedom. All right, so that was a design. Of course, you need a MV machine to grow them. So this is the MV machine in my group. Since I am talking about this MV machine, I just want to say a few words. So this machine has been recently upgraded. So it used to be a 2-chamber 3.5 machine. Okay. So then 2 years ago, I spent quite a bit of money upgrade one of this side to become a 2.6. Okay, so I have a 2.6 on this end, a 3.5 on the other end. Right. So this machine is very, very capable to grow all kinds of materials as I listed early on. Okay. So we have grown quite many samples. So here I just summarized 2 sets. We designed 2 sets, and so this is a set growing in my group. So this set were grown by IQE, one of the industrial vendors for MBE growth, and they are very well funded by U.S. Government to grow type 2 superlattices. So basically, they give us a very good benchmarking of our material quality and etc. So now you can see, indeed, with both MBE machines, we can grow very high quality materials. So this is a typical X-ray diffraction pattern. So you can see this is a substrate peak, gallium antimonide. So this is zero order peak of the superlattices. So all these are the so-called satellite peaks. So you can see they are very distinctive, and it's in good, reasonably good agreement with the simulation. But if you blow this pattern out, you can see very beautiful pendulosum fringes. So these pendulosum fringes corresponds to the total thickness of our layer. So you can only see this if all the interfaces are very sharp, and if all the compositions in each layer, all the layers are the same. Then you can see these pendulosum fringes. Otherwise, normally you don't see them. So now you can see these fringes are almost perfect, like the theory predicts. So we are very, very pleased with the quality of the samples. And also we can if you fine tune your growth condition, basically you can make it a so-called almost a perfect lattice match. The short period of superlattice is overlap with the substrate peak. It's almost right on, right? So and that was the MBE part. So now this is the typical TEM image. You can see the surfaces are very well defined, and the materials are very, very uniform. And so now, as I said earlier, we have grown many different samples, and because the theory says we can cover a very, very broad spectral range. So indeed, so our samples can cover from 4 micron up to 13 micron. Right. So basically, just by changing the thickness, so we can cover such a very broad range. Right. So, well, we change the thickness, but also the composition a little bit, so we can cover the entire range. And also, as theory predicted, when you go to longer wavelengths, the wave function overlap getting smaller, and then the PL intensity actually decreases. And so this is all in agreement with the theoretical prediction. So you can see the middle infrared 4 micron give you much stronger PL intensity. 12 micron is getting much weaker. All right. So now, because as I said earlier, so this our approach. Okay, we don't have a gallium, so that's why we're gallium free, and the interface is much simpler. So the growth is much easier for this type of superlattices. So you can see within 4 runs we can reach the lattice match condition. Then we can maintain that through the campaign for many runs. But if you look at the other approach, indium arsenide, gallium indium alpha, so this is work was done by industrial growers as well as research institutions like JPL and the Naval Research Laboratory. And you can see it will take a long time for them to get to the optimum growth condition. You can see it takes them typically over 30 runs. Right, so you can see that there's a big difference here. So all this calibration is very expensive. So you can see, so this approach really saves a lot of effort.
Do you understand physics why gallium is so bad?
Yeah, I will. Yeah, I will say a few words about that. Okay, so now, so first let's look at the physics. So what's the difference between these two approaches? All right, so there are a few very interesting papers published early on. The theoretical work was published by Chris Grind and Michael Aflate in 1995, and some experimental work published by myself and my collaborators. And so you see that at that time, Chris was doing a lot of calculation. So I remember he showed me some of the preliminary results, very exciting. So then I told Chris, I said, hey, Chris, why don't you guys look into this approach? And because I see some very high quality single crystals. So I think they did some calculation, then they compared this. So that's why they mentioned my name in their acknowledgement. So now you can see from theoretical point of view, so these two material systems give you very similar so-called D star. Right? Basically, that's a parameter to describe the performance of photodetectors. And so this is the mercury cadmium telluride theoretical limit. So the theoretical limit of type 2 superlattices, according to this paper, will be better than mercury cadmium telluride. So that's why this paper generated a lot of interest in the detector community. But unfortunately, we haven't reached the theoretical limit yet. So all the type 2 superlattices device cannot beat a mercury cadmium telluride yet. Now, from the absorption coefficient point of view, you can see the mercury cadmium telluride has a much higher absorption coefficient, which is good for infrared detectors. And then this gallium-containing or indium arsenide, indium gallium antimonide has also higher absorption coefficient than the so-called gallium-free, because effective mass of that super is much higher than indium arsenide based one. All right. So this is the theoretical prediction. And now, from device point of view, okay, from device point of view, so what will be the ideal parameters for device? All right. So for infrared detectors, obviously you want to have very low dark current, right? Because the dark current limits the minimum signal you can detect, right? So you can never detect anything below the dark current. So the dark current can be expressed in a typical photodetector as this. So this Ni is this intrinsic carrier concentration, obviously determined by band gap, and then the D is the absorber thickness. So the Nd is like a doping. Tau is the carrier lifetime. So from here you can really tell, right? So if your layer is very thick, then this dark current will be very high, or if your carrier lifetime is very short, the dark current will be very high, right? So from this you can tell for high performance detector you want to have very long carrier lifetime, right? So this formula tells you quite clearly, right? So now you can see. So this line is so-called rule 07. So basically this line tells you the best MC detector performance, right? People can get. So all these dots tells you the type 2 superlattices. So you can see all these dots are well above this MCT line. So that means that we have much higher dark current, right? That means poor device performance. So in order to improve the device performance, obviously we need to really increase the lifetime, because for mercury cadmium telluride, the lifetime can be very long. It can be on the order of a few microseconds. Okay, but for the type 2 superlattices, before all work, is on the order of 30 nanosecond. Okay, so it's about a three order of magnitude difference. Yeah. So we use a PL structure, first time demonstrated that using this so-called gallium-free superlattices, you can really dramatically improve the lifetime, right? So this is a typical PL spectrum at 8.2 micron. So it's around 0.15 EV, okay, very narrow gap. And so this is a very interesting result we reported 2011. So now you can see we have reached 412 nanosecond. So which is more than 1 order of magnitude longer than this conventional type 2 superlattices, typically 30 nanosecond. So I want to emphasize this 30 nanosecond has been the record for probably more than 2 decades, right? So basically it's saturating. So this is kind of like a breakthrough. So we break that barrier with a 1 order of magnitude improvement. And so now the other interesting thing is that if we believe that, for instance, this is our PL measurement of our sample, and if you monitor the PL intensity, integrated intensity, and if you cool the sample down, so below a certain temperature, so the intensity doesn't increase anymore. So we believe that's when you reached almost 100% internal quantum efficiency. So that's why the PL will never go up. You already get all the photons out. Okay, and so based on this, we believe that this structure, this gallium-free structure, is limited at 77 Kelvin here. It's probably limited by the Schottky-Riedel non-Riedel recombination. Now come back to your excellent question. So why? So this Gallium is important, right? So now why these superlattices gives such a long lifetime, and this one doesn't? So we believe that this is the reason, because it's known that the defects in the marsenite materials generate electrical energy states in the conduction band. Okay, and so those defect states will not affect much of the minority carriers inside of these superlattices. But for the other superlattices, and we all know that when you have a defect in gallium antimonide, they typically generate energy states in the middle of the forbidden gap. So if you have a lot of energy states in the forbidden gap, for instance, this is the superlattices, right? The effective gap is this two dash line. So those energy levels will act as a Schottky-Riedel recombination centers. So that will kill the carrier lifetime. So that's what we believe. So as some theoretical calculation shows that probably is the case. Yeah. And so it's amazing. So we are very pleased with these results. Yeah. All right. So of course, we have to further convince people. Hey, show me a device. So we demonstrated the first device, which is called NBN photo detectors. I'm not very sure if everybody familiar with NBN. This device is new to me, a few years ago. So the NBN structure is very, very smart, but very simple idea. So the idea is very simple. So what you do, you get a photoconductor, and obviously you know that when you have a photoconductor, you always have a dark current. And so now you say if it's intrinsic semiconductor, you have equal amount electron and the holes, right? But for instance, if you dope this, then you can increase the electron concentration, you reduce the hole concentration, but then this electron is conductive. So the NBN is very, very, very smart. So they say, okay, you dope N-type, then you put a barrier. Okay, you put a barrier only for the electrons. All right, you don't have any barrier for the holes. So now, because you put a lot of electrons in the conduction band, so from the basic physics, what we know, right, N dot P, right, equals Ni squared. So you have a very small amount of holes. Right. Now, if you have a barrier which stops the conductivity of electrons, so then your heavily doped semiconductor will have very low conductivity. So that means that when you excite just a few holes into the valence band, you will see the difference. Right? So this really overcome the conventional photoconductor design. So this device shows some very promising potential. So we use the type 2 superlattices. We demonstrated the first NBN using this kind of type 2 superlattices. So now you can see, indeed, we can detect up to 13 micron, and so this is the 0.25 amp per watt response. So this is a kind of typical diagram, IV diagram, can tell you the dark current and the overall device performance. So I won't get into too much details. So basically, we just want to show people here that indeed we have very, very low dark current. Okay, this dark current is probably one of the best reported for type 2 superlattices, and at a 77K. So it's confirming that indeed we must have very long carrier lifetime, as I said earlier. All right. So that is the thing. So here are some details. Probably I skip this. Okay. All right. Do I have a total 45 minutes or 1 hour? 1 hour. Okay. I have probably another 10 minutes. All right. Now I just want to discuss with you some very interesting idea we demonstrated. Because now we can make multi wavelengths detectors, and we really want to demonstrate the multicolor detectors, right? I mean, everybody probably these days is using multicolor detectors, like our camera, because you see that they like use CMOS. They use this kind of way to do they use a filter layer, right, to get a multicolor. I mean, for the visible range. Okay, but for the infrared application, of course we use different wavelength materials. But now, I just come up with another way to do multicolor detection. Because look at this. If you use this approach, you have to add different filters at a different region, right? So basically, you get this detector, so each pixel can only detect one color, right? So the utilization of your wafer is not the best, right? But fortunately, silicon is cheap. No, we don't care much. But for the infrared, the material is very expensive. So the way I do the color selection is like this. Actually, this is very interesting. So this is inspired by how people test multi-junction solar cells. So how people test a multi-junction solar cell is that because of the solar cell triple junction, they are very much like 3 diodes connected in series by 2 tunnel junction. So if I want to characterize the middle junction, it's very difficult because I cannot take that junction out. So the only thing I can measure is the voltage across the overall device and also the current. So the only way I can really characterize this device, I have to apply a optical bias. So how does it work is that you can apply optical bias. So basically you can apply optical bias on this diode, optical bias on this diode. So then the total current is limited by the middle diode. So you are measuring the current going through the middle diode. Right? So that's the way people normally characterize the multi-junction solar cells. So I take advantage of that. So now if you look at this, so if you have imaging system, so you get 3-color photo detectors. So you optically bias the top one, optically bias the bottom one. So then only the middle one detects the photon, right? So that means that if you have a photon which can be absorbed by the middle one, you will see response. Or otherwise, you don't. For instance, you have a photon coming in absorbed by the top detector, so then you don't. It does not change the current. Okay, because there's no photon can be absorbed by the middle detector. So by doing so, you can see. So this is your so-called response curve, right? So now you can see. So with this wavelength range, only the top detector response. With the other wavelength range, the middle one response, and the bottom one, the other one response. Right? So now you can detect, different colors. So by only changing the bias, instead of changing the optical bias using LED, so now you can using a kind of same device to detect all different wavelengths. So in theory, you can detect 5, 6, 7, as many as you want. Right. But the other way is almost is very difficult to do that. It's kind of because because say silicon can do that because the visible range is very narrow, right? So if you have to do, say, like, I think our ambition is that I will build a multicolor detector which can detect the UV and the 2 long wave infrared. All the optical band I can all detect with one epitaxial growth, right? So that's why we want to do the 2.6 and 3.5 integration. So for this multicolor detection. And also this kind of detector gives you a very large dynamic range because people had some concern, how about the dynamic range? So there's no problem for dynamic range, you can see. So this is the laser power input, and this is the output. You can see multiple order of magnitude easily, not really a problem. Yeah. All right. So since I talk about this integration, so I just want to show you some of our preliminary results. And so again, let's look at this diagram again. So now you can see if you focus on gallium antimonide or indium arsenide, so you can have a lot of wide bandgap semiconductors available. So these materials are amazing, and they are all zinc blend, and all direct bandgap is perfect for optoelectronic devices, and they also have thermal coefficients, very similar thermal coefficients. So they don't have a thermal mismatch, right? So that means that you can grow them on top of each other. And this is one of our first try. We published in 09. So we grow zinc telluride and gallium antimonide. You can see. So that interface is really beautiful, really beautiful. And because of the lattice constant of zinc telluride is very close to gallium antimonide. So the mismatch is only 0.13%. That's better than aluminum arsenide and gallium arsenide. Okay, so it's very, very good. And so, of course, you don't see misfit dislocations, right? And also the other thing we demonstrated is that probably some of you may be familiar with the so-called VCSEL, vertical surface emitting lasers, because if you can build this kind of laser, the light will come out from the top, not from the edge, right? And this device is very small, and you can do all kinds of things. Okay, but the critical part, one of the critical parts, is the so-called DBR. Now, if you want to do middle infrared, so if you use a conventional semiconductor, so you have to grow very, very thick DBR, which is not practical. But if you use a 2.6, right, because the zinc telluride and the gallium antimonide, so the refract indexes are very different. So the delta N is about a 1.2 at 2.5 micron. So we only need to grow, say, like this one, like a 4 pairs, and this is a 4 pair. And so actually, the other one I show you later is a 7 pair. So we can already get a 90% reflectivity, which is very, very good. So the total thickness is only 3 micron. Yeah. That's here. So now you can see this is a 7 pair. So the dark line is experimental data, and the red line is theoretical simulation. So you can see, indeed, we can get to 90% reflectivity using only 3 micron thickness somewhere there. So this is very, very good. Okay, so this is very, very good. So here's a simulation about 1 pair, 2 pair, 3 pair, 7 pair. So this is okay. We can all get 99% reflectivity, and also a very broad stop band. Right, the stop band width, as you probably know from optics, is also proportional to the delta N. So the larger the stop band, the better, or you have wider tunable range. So I hope that someday we can demonstrate a tunable, 2.5 micron VCSEL, then you can really detect all the optical absorption of atom sphere or some other medium. Okay, so so that's the current results. So I think I almost to the end. So I just want to show you what we plan to do in the future. And so now you can see that because of the material system we can have, that we can really integrate a lot of colors all together. For instance, just we can add UV and visible using 2.6 materials, and we can add near infrared like a gallium antimonide. Then we have the type 2 superlattices of middle infrared, long wave infrared. So we can put all this detector together on a lattice matched substrate, which is very, very rare to get. So this is basically our kind of our dream detector. Someday we should be able to demonstrate that. With that, I think here is just as a summary. So we successfully demonstrated this long wave IR gallium-free type 2 superlattices, which shows very, very long, record long carrier lifetime, and also some low dark current devices. And we also proposed and also demonstrated a novel way to do focal plane array using optical addressing. And so hopefully we can integrate more than 4 colors together on a single substrate. I think that's all. All right. Thank you for your attention. Yeah.
Other questions from the audience?
How much did you have to clean up your chamber when you went from C5 to C6?
Yes.